This lecture is about the syntagmatic relation discovery and conditional entropy. In this lecture, we're going to continue the discussion of word association mining and analysis. We're going to talk about the conditional entropy, which is useful for discovering syntagmatic relations. Earlier, we talked about using entropy to capture how easy it is to predict the presence or absence of a word. Now we address the different scenario where we assume that we know something about the text segment. So now the question is, suppose we know eats occurred in the segment. How would that help us predict the presence or absence of a word like meat? And in particular, we want to know whether the presence of eats has helped us predict the presence of meat. And if we frame this using entropy, then it would mean we are interested in knowing whether knowing the presence of eats could reduce the uncertainty about the meat or reduce the entropy of the random variable corresponding to the presence or absence of meat. We can also ask the question, what if we know of the absence of eats? Would that also help us predict the presence or absence of meat? So these questions can be addressed by using another concept called conditional entropy. So to explain this concept, let's first look at the scenario we had before, where we know nothing about the segment. So we have these probabilities indicating whether a word like meat occurs or doesn't occur in the segment. And we have the entropy function that looks like what you see on the slide. Now suppose we know eats is present. So now we know the value of another random variable that denotes eats. Now that would change all these probabilities to conditional probabilities, where we look at the presence or absence of meat given that we know eats occurred in the context. So as a result, if we replace these probabilities with their corresponding conditional probabilities in the entropy function, we will get the conditional entropy. So this equation now here, shown here, would be the conditional entropy, conditional on the presence of eats, right? So you can see this is essentially the same entropy function as you have seen before, except that we all the probabilities now have a condition. And this then tells us the entropy of meat after we have known eats occurring in the segment. And of course, we can also define this conditional entropy for the scenario where we don't see eats. So if we know eats did not occur in the segment, then this conditional entropy would capture the uncertainty of meat in that context, in that condition. So now putting different scenarios together, we have the complete definition of conditional entropy as follows. Basically, we're going to consider both scenarios of the value of eats, 0 or 1, and this gives us a probability that the eats is equal to 0 or 1, basically whether eats is present or absent. And this, of course, is the entropy, conditional entropy of meat in that particular scenario. So if you expand this entropy, then you have the following equation, where you see the involvement of those conditional probabilities. Now, in general, for any discrete random variables x and y, we have the conditional entropy is no larger than the entropy of the variable x. So basically, this is the upper bound for the conditional entropy. That means by knowing more information about the segment, we won't be able to increase the uncertainty. We can only reduce the uncertainty, and that intuitively makes sense, because as we know more information, it should always help us make the prediction, and it cannot hurt the prediction in any case. Now what's interesting here is also to think about what's the minimum possible value of this conditional entropy. Now we know that the maximum value is the entropy of X. But what about the minimum? So what do you think? I hope you can reach the conclusion that the minimum possible value would be 0. And it will be interesting to think about under what situation we'll achieve this. So let's see how we can use conditional entropy to capture syntagmatic relations. Now, of course, this conditional entropy gives us directly one way to measure the association of two words, because it tells us to what extent we can predict the one word given that we know the presence or absence of another word. Now, before we look at the intuition of conditional entropy in capturing syntagmatic relations, it's useful to think of a very special case listed here. That is the conditional entropy of the word given itself. So here we listed this conditional entropy in the middle. Right? So it's here. So what is the value of this? Now, this means we know whether meat occurs in the sentence, and we hope to predict whether the meat occurs in the sentence. Now, of course, this is 0 because there's no uncertainty anymore. Once we know whether the word occurs in the segment, we already know the answer of the prediction. So this is 0, and that's also when this conditional entropy reaches the minimum. So now let's look at some other cases. So this is a case of knowing the and trying to predict the meat. And this is a case of knowing eats and trying to predict the meat. Which one do you think is smaller? Note that a smaller entropy means easier for prediction. Which one do you think is higher? Which one is smaller? Well, if you look at the uncertainty, then in the first case, the doesn't really tell us much about the meat. So knowing the occurrence of the doesn't really help us reduce the entropy that much. So it stays as fairly close to the original entropy of meat. Whereas in the case of eats is related to meat. So knowing presence of eats or absence of eats would help us predict whether meat occurs. So it can help us reduce the entropy of meat. So we should expect the second term, namely this one, to have a smaller entropy. And that means there is a stronger association between meat and eats. So we now also know when this W is the same as this meat, then the entropy, conditional entropy, would reach its minimum, which is 0. And for what kind of words would it reach its maximum? Well, that's when this W is not really related to meat. And like the, for example, and it would be very close to the maximum, which is the entropy of meat itself. So this suggests that we can use conditional entropy for mining syntagmatic relations. The algorithm would look as follows. For each word, W1, we're going to enumerate over all other words, W2, and then we can compute the conditional entropy of W1 given W2. And we sort all the candidate words in ascending order of the conditional entropy because we want to favor a word that has a small entropy, meaning that it helps us predict the target word W1. And then we can take the top ranked candidate words as words that have potential syntagmatic relations with W1. Note that we need to use the threshold to find these words. The threshold can be the number of top candidates to take or absolute value for the conditional entropy. Now this would allow us to mine the most strongly correlated words with a particular word W1 here. But this algorithm does not help us mine the strongest k syntagmatic relations from an entire collection, because in order to do that, we have to ensure that these conditional entropys are comparable across different words. In this case of discovering syntagmatic relations for a target word like W1, we only need to compare the conditional entropies for W1 given different words. And in this case, they are comparable, right? So the conditional entropy of W1 given W2 and the conditional entropy of W1 given W3 are comparable. They all measure how hard it is to predict W1. But if we think about the two pairs where we share W2 in the same condition, and we try to predict the W1 and W3, then the conditional entropies are actually not comparable. Well, you can think about this question, why? So why are they not comparable? Well, that was because they have a different upper bounds, right? So those upper bounds are precisely the entropy of W1 and the entropy of W3. And they have different upper bounds. So we cannot really compare them in this way. So how do we address this problem? Well, later we'll discuss we can use mutual information to solve this problem.